the next step we're going to take, now that we have talked about the idea of moles and balanced chemical reactions, is what we call stoichiometric calculations. And the idea here is that if we have a balanced chemical equation, we can use it to calculate amounts of products or reactants that we would either need or expect based on that balanced chemical equation. So we can do calculations such as, say, I know that I have 15 grams of a reactant that I'm starting with. How much of a particular product am I going to get from that? That might be one kind of question that you're able to answer with stoichiometric calculations. Another might be, you need a certain amount of product. Say I know at the end result I need 20 grams of product. Do sort of the backwards version of this calculation. How much of my reactants do I need to start with in terms of mass? And what can be a little tricky here is remembering that in all of these calculations, the key to all of this is that a balanced chemical equation does not tell you anything about masses. Instead, it tells you about the relationships of moles. So we're often measuring or given values in grams or even in volume, and then you use density. But ultimately, if we want to compare reactants and products, we have to do it on a mole-to-mole basis. And so your balanced chemical equation you can kind of think of as this is giving you a conversion factor for the particular chemical reaction that you're considering in a stoichiometry question. So I think the best way to make this make more sense is to do an example calculation. And I actually really like the one that's in your textbook because it deals with something that we're all familiar with, which is when we burn fossil fuels, when we do a combustion reaction, continuing on from last video, we produce carbon dioxide, right? That carbon gets turned into carbon dioxide. And so we care a lot about for a certain amount of fossil fuel that we combust, how much mass of carbon dioxide are we producing? And that's the kind of question we can answer with stoichiometric calculations. And so let's go ahead and give myself some space here. Let's do this for a reaction that approximates what happens in a vehicle. So we use gasoline, and a lot of gasoline it's made from a mixture of things. So we are simplifying things a bit here. But we can consider it as approximately, on average, having a hydrocarbon with 7 carbon atoms in it. So we'll approximate that as this molecule called heptane, C7H16. And this is going to undergo a combustion reaction in an internal combustion engine and produce CO2 and water. And so a question you might have is, for a given mass of heptane, how much CO2 is produced? Or for a given volume? Well, let's do it as a volume. Say for every 1 gallon of gas, if we combust that and the reaction goes to completion, how much CO2 are we going to have? And we'd like that in terms of a mass of carbon dioxide. Okay, so how are we going to approach this question? Well, the very first thing we need is a balanced chemical equation. So let's go ahead and write out what we know, C7H16. This is going to be a liquid. We know it's going to react with oxygen because this is a combustion reaction, and it's going to produce carbon dioxide and water. And we'll say, we'll say it's a liquid. It doesn't particularly matter for this example. Okay, so this is the unbalanced equation. Let's start with carbon. You'll find that for combustion reactions, starting with involving hydrocarbons at least, starting with carbon is usually a good starting place. So we have 7. Let's use red instead. We have 7 carbons over here. So we're going to need to, on the right-hand side of the equation, we only have 1 carbon. So we're going to have to balance that with the 7 here. Now let's do hydrogen next. We have 16 hydrogens on the reactant side. So we're going to need 8 waters to get our 16. And now that's balanced the carbon and hydrogen. Oxygen's not balanced. So on the right-hand side of the equation, we have 14 in this molecule, 8 here. So overall, we have 22 oxygen atoms. So that means we're going to need 11 oxygen over here. Okay, now for our question, let me change this color here. We'll use yellow. So for our question, the coefficients that matter are the coefficients for our heptane, not pentane, and our carbon dioxide, because we're only considering those. But because we have the oxygen and water coefficients, we could use those as well. But when I say that this gives us a conversion factor, it gives us a conversion factor in terms of numbers of molecules or, and crucially, moles. So what that tells us is that when this reaction occurs, 1 mole of heptane, C7H16, will give us, or be equal to, once the reaction is complete, 7 moles of CO2. And it tells us nothing about mass, but it does tell us about moles. All right, and so that is one of the key things here, is that we have our relationship now between our C7H16 and our CO2. Some other things we're going to need. Number one, we said that we have a gallon of gas. So I'm going to set up this calculation, and this will continue on in another video, but I just want to get all the setup done here. We have 1 gallon of gas. We need at least an approximate density to be able to get this into grams. So your textbook gives a density of density of gasoline is about 0.73 grams per milliliter. That's not something I would expect you to know off the top of your head, but we need a value here, right? And then we also need to know how much a gallon is. So a gallon, 1 gallon. Again, not something you can look up, but 1 gallon is 3.785 liters. And another conversion that's going to come up that will be useful to remember is that 1 milliliter and actually, we don't need to do that because our density is already given in terms of milliliters, but just remember that a milliliter and a cubic centimeter are the same thing. So if you see a density in grams per cubic centimeter, that's the same as grams per milliliter. Okay, so we will continue this in the next video, where we're going to take our 1 gallon of gas, given this density, and given this volume for a gallon in terms of SI units, and use that to find how many grams of gas that corresponds to, and how many moles of gas that corresponds to, and then use our balanced chemical equation to continue this calculation.